formed very early.
And Sabina, do you have anything you'd like to add too?
No, I mean, I thought that was great.
It was a great answer. Now we have a question coming in about the studies. Dan on Twitter asks, findings say the crust of Mars is likely highly enriched in radioactive elements that help to heat this layer at the expense of the interior. What radioactive elements are likely? How do you detect that? And why are they at the expense of interior? I can repeat that. I know that was a lot to.
Amir, you want to talk about it, or I can talk about it too, but
I don't know. In any case, I would have to have the question again, please, Raquel.
Yes, of course. Findings say the crust of Mars is likely highly enriched in radioactive elements that help heat this layer at the expense of the interior. What radioactive elements are likely? How do you detect that? And why are they at the expense of the interior?
Okay. Yeah, so the main radioactive elements we have on the crust would be uranium, thorium, and potassium, and that's the same on Earth and pretty much the same on all terrestrial planets. We say that they are enriched because we have, prior to InSight landing on Mars, we had this, there was this previous, in the early 2000s, this Mars Global Surveyor satellite mission that was orbiting Mars and was measuring. It contained a so-called gamma ray spectrometer, which basically measures the number of gamma rays that are emitted from the surface, and gamma rays are emitted from radioactive decay of these radioactive elements, right? So prior to InSight, we had this idea of the radioactive element content, but of course only on the surface, right? And now what we did with InSight is, of course, to you look inside the planet, you look inside the crust. So I mean, again, we have to be aware that InSight doesn't directly see, radioactive elements. InSight is all about seismology, but you can indirectly estimate from the seismic data and from the models we produced by, running so-called, models that sort of try to mimic the evolution of Mars over 4.5 billion years, right? And what you end up with when you run these so-called evolution models over 4.5 billion years, you end up with something today, which is, the models will predict a crustal thickness. It will predict a lithospheric thickness, and it will predict temperatures. And those things from these modeling studies, you can compare with what we have predicted from InSight. And when you do that, you find that, in order to predict the crustal thickness that InSight has seen and the lithospheric thickness, the crust of Mars needs to be enriched in these light elements. If not, you don't get the right, crustal thickness and lithospheric thickness and temperature and stuff like that. So relative to what we knew, from the surface, from this Mars Global Surveyor, the radioactive elements have to be, there are more of them, right? But that means, you can't just get rid of MGS, because MGS actually measured something on the surface. But it means that, as you inside the crust, deeper down in the crust, you have rocks, different type of rocks from the surface that contain more radioactive elements, right? That contain different,
Yeah, and the key element there is that there's, we have estimates of how much of these heat producing elements were available to Mars based on estimates of the solar material that created Mars. And so if you're putting more in the crust, it means you're taking more out of the mantle. So this, when you melt the mantle to create the crust, you are shoving those heat producing elements into the crust, and therefore relatively cooling down the mantle. So you don't have as much heat production in the mantle. So that makes the mantle a little more cool, gives you a thicker lithosphere, all of that, because we're putting all of those heat producing elements in the crust.
Maybe I could add one thing to what. Maybe I could just add just a final thing is that's just to follow up to what Mark said. I mean, and the real way to get at the how many radioactive or the radioactive element content of the crust would have been to put that heat flow probe on there, which we did, but unfortunately it never reached the depths that it had to in order to measure the heat flow that we would have needed in order to put constraints on the radioactive element content of the Martian crust and the heat flow and everything beneath it, really. So that was a very unfortunate occurrence that it didn't function, of course.
But I'd like to thank you and Mark for that really detailed answer to the question. We are getting some great conversations going, and we have Niels on YouTube who is asking, are any of InSight's findings likely to influence the science mission of Perseverance or future Mars missions? Mark, would you like to try?
Yeah, I mean, Perseverance is sampling surface material, and we're not directly affecting that. We're looking deep inside, and the deep inside isn't at the surface. So Perseverance is going to make their decisions on what to sample at the surface based on orbital observations and what they see as they drive around. And so we're not going to probably have any direct impact on Perseverance necessarily. But in terms of future missions, things we'd like to see on Mars, I mean, so Amir just pointed out, we'd still love to get a heat flow measurement. That would be a great future mission, and we now know more about where quakes happen near InSight. But as Sabina said, there's also likely to be seismicity associated with Tharsis. So we can imagine putting seismometers in different places on the surface, and we're constraining better where we'd like to do that in order to better increase our understanding of Mars.
And if I can add just a little bit to that, even though a lot of the basis of the mission and the focus of the mission is the seismicity and understanding the deep interior, there are instruments on InSight that look at the surface and look at the atmosphere. So we have cameras that can tell us about the surface, and that helps us understand the geology and how things, what's the very, very top layer of the surface, what's it all about. And even though we're learning that from the InSight lander location, that's one data point, but it's an important data point to try and understand all of Mars. And we learn about the atmosphere of Mars. It turns out to be important to kind of take out the atmospheric signals from the seismicity signals. And that, again, can kind of be used with all the atmospheric information we have on Mars. And all of that's going to be helpful for any mission to the surface of Mars in the future.
We do have time for a couple more questions. So we have Jesse on Facebook who asks, scientists believed the factors like the moon's gravitational push and pull, the planet compressing, or meteor impacts caused quakes. How likely is it that more than one factor could be causing Mars quakes?
I mean, I can talk about that briefly. I mean, quakes are an expression of stresses and forces within the crust of Mars, and undoubtedly that those stresses are the combination of lots of different things. I got at that earlier with talking about the overall slow cooling and the weight of big things sitting on the surface of Mars, and that's even including weight of the ice caps at the North and South Pole. All of those things are putting pressures on Mars and changing the stress within the crust. So everything is a combination. There's no one single answer to what's causing the quakes.
Maybe I could just add, I mean, it's true that for the moon, we found these so-called deep moonquakes, which were, apparently they correlated very well with the tides that were raised on the moon by the Earth. And I suppose the question is a little bit the same here. Could, the Martian moons influence Mars quake activity? but that's actually pretty simple to answer. And I mean, not me personally, but people have looked at for, correlations between the tides raised by I mean, Deimos is too far away and it's too small to raise any significant tides on Mars. Phobos does raise a tide, but it wouldn't be strong enough to produce any strong quakes or stresses in the crust of lithosphere or the interior of the planet that would, release any type of or produce any type of seismicity as we see it. At least we haven't seen that yet.
And we have time for 2 more questions. So Sonia on Facebook asks, what's the mission going to look at next?
Maybe I can take a stab at that. I mean, one of the interesting things with regard to the core, Sabine has been talking a lot about the magnetic field, is of course the question of whether Mars has a solid inner core like the Earth has. Likely it doesn't, but then again, we don't really know, right? We have to go down and dig into the data and look for it. This is very likely going to be a very difficult problem, and another one of those things where you have to look for the needle in the haystack. But if Mars contains, the equivalent of an inner core, then it is in the data, and it's about trying to extract that signal, really. But that would be a major finding.
Mark, Sabina, would you like to add to that?
Go ahead.
So yeah, I agree. I'm most interested in seeing whether or not we're going to get some information about if and how big would a solid inner core be in Mars. And I think that means, we're waiting for bigger earthquakes as Mars quakes as well. That would be very helpful, and from the right location so that we can see them at the InSight lander. So everyone cross your fingers and keep wishing and hope that this happens.
Yeah, and I just say we're continuing to listen. We're recording right now, so we're getting new quakes all the time, and there's still a lot of mysteries about the quakes themselves. The ones we're talking about that we've used for these studies are all a type of quake that we call either low frequency or broadband, and these look a lot like earthquakes in a lot of ways. We have a pretty good understanding of how they work, but there's also different types of quakes we're seeing that are called. We have a whole suite of names for them: high frequency, very high frequency, even super high frequency, and they're all different, and they have lots of weird properties that we don't totally understand. And so, the more of that data we can get and look at the statistics of when they happen and all of that, those are all a lot of questions we'd like to understand. And I don't have a quick answer for you for understanding all of them yet. And hopefully after some more data, we'll have better answers for that sort of stuff.
Well, this is a good segue into our
ad.
Oh. Go ahead.
Sorry. I'll just also quickly add that one thing that's been great about the length of time of the InSight mission is that, so Mars's year is about twice that of Earth's year, the amount of time it takes to go around the sun in its orbit. And so we're also able to now, because we've been there for so long, look for seasonal effects, look for, since we have repeats of the Mars seasons. And so I think that's also an interesting thing we're going to be looking at in the future.
That kind of segues into this final question that I have that I want each of you to quickly answer. Joe on YouTube asks, based on all your findings, what would be the next generation of instruments you would like to see sent to Mars for further understanding? Oh, I see Sabina getting excited about that one. Would you like to go first?
Sure. I think that there is a whole lot of opportunity in things like drones or helicopters, right? We have Ginny there right now. The ability to move around and get information from different places on the surface, that would be really great in terms of learning about the next generation. We want to have information about the magnetic field, the surface properties, the gravity, seismicity. We want it from a lot of different locations. So the more we can do that, the more we're going to learn about the interior of Mars.
Like to go next, Mark?
Sure. Yeah. So for me, I 100% agree with Sabina that more at more locations, and connected with that, one of the big challenges we have in InSight is that we're trying to locate events with one station. And if you took an intro class, they teach you somewhat incorrectly that you need three stations to locate a quake. We've proven that you can do a lot with one station, and we can locate quakes with one station. But the fact remains, it's still a lot easier to do a lot of seismology if you have more stations. And so, there are options. You could imagine a global network of stations that are really sensitive and are measuring like what we're doing, and just really nailing down the global picture of what's happening with seismology, and then maybe looking at variations in crustal thickness. Or you could imagine local networks that are looking at areas of interest like Cerberus Fossae or Tharsis, where you could get away with maybe having less sensitive stations because you're sitting right where quakes are active, and so maybe you could have cheap landers with less expensive sensors, and get networks and really get into understanding locations of these small events that we can't really locate with one station and with InSight.
And then Amir?
Yeah, I think I share the optimism of Mark and Sabine, but I think we still have, in the light of what we've learned now and what we've seen with a single station, and we've done a lot with a single station, right? And it's amazing, it's outstanding, the stuff that we've been able to do. But I still think that we have to keep in mind that we have all of these different geophysical methods. Like you look at magnetic fields and gravity and stuff like that. But we have to keep in mind that seismology is the gold standard in the sense that it is the geophysical method that has, that gives you the highest resolution when you look inside a planet. And for that reason, we've been talking a lot about. I don't want to make this a long story, but we've been talking a lot about the broadband seismometer, but there was also a short period seismometer on there, which is based on MEMS technology, and it's light, it's compact, it doesn't weigh anything, and you could send stuff like that. But unfortunately, what it's turned out is that a lot of the stuff, the Mars quakes that we've been using to look inside the planet have really only been picked up properly by the broadband seismometer. So I think going back and doing arrays and tens of station stuff, of course we'd love to do that, and we'd like to dream about magnitude 5s and 6s. But these particular, the seismometer that Mark talked about and he showed on the images, they are built specifically and in laboratories for these types of missions, and it's not something that's simply packaged and moved elsewhere, right? So it's a little more difficult than that if you want the type of stuff that we've been able to do on Mars with InSight. But I think, as I said in the beginning, I think the fact that we've been able to do so much with a single station is really is going to pave the way for future missions, because you can just take a single station and move from there. Place it on a different location of the planet, of course, but
we're all dreaming of big
right.
Mars quakes, like you said. That is all the time we have today. And I'd like to thank everyone for their questions, and thank you to the team for chatting with us today. Now, for more information and to stay up to date with the mission, visit mars.nasa.gov/insight and follow @NASA Insight on Twitter and Facebook. Thanks for watching.